Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very fortunate to be joined by Scot Rafkin, who's come across to us from Colorado, from the Southwest Research Institute, where he works. He got a BS in atmospheric sciences from UCLA, and then a master's and a PhD at Colorado State University in atmospheric sciences. And then following his PhD, he did postdoc at NCAR in Colorado and moved then to the Bay Area for a few years where he was working as an assistant professor at San Jose State. Then he moved back to Colorado to Southwest to head up the a new Mars GCM team at SWRI. He has worked on atmospheric hazard assessment for the Mars exploration rovers, obviously very successful because they got through the atmosphere, no problems. And he's also done the same work for the Phoenix lander, and he is also involved in the Mars Science Laboratory as a project scientist on the RAD team. He, as I mentioned, is head of a team that's currently pumping out work on the Martian atmosphere at SWRI. Today he's going to talk to us about his thoughts on the future evolution of global climate models at Mars. So if you'll join me in welcoming Scot.
So we're on. You can hear me, right? Okay. All right, thanks for the introduction, and it really is my pleasure to be here at the SETI Institute. And I appreciate the opportunity to tell you about some of the research I've been working on lately on Mars. It's a very broad and diverse audience today, so I'm going to pitch this to be very conceptual rather than looking at bunches of equations and things. So if you spend your life working on the Mars atmosphere, I apologize that I hope I don't put you to sleep, but I think you will find some interesting tidbits in here, and certainly I'd be happy to talk with you afterwards. But I want to make sure that I have a talk that everybody can enjoy and appreciate, hopefully. Now, I had a lot of questions about the title slide, so I'm just going to say something real quick about this. This is an image of Mars taken from orbit, and what you're looking at is this blob here in the middle is a dust disturbance. It's the little local dust storm. These are fairly common on Mars. We hear about the big global dust storms that happen on Mars, but those only happen every few years. These are very common. They happen almost on a daily basis, and so these sort of things going on. And then above that, you can actually see some clouds that are sort of whitish looking. These are water ice clouds. So yes, there is water on Mars. We've known about it for decades and decades and decades, just that it's all frozen. Okay, so this is a common thing on Mars. Okay, so I said I was going to kind of start conceptually, and so this is where it all begins when you're talking about weather and climate, which is that the sun shines on a planet. Okay. And as that sunlight, in this case I got a picture of Earth, but it could be Mars, it doesn't really matter. When it shines on that planet, it matters where you are. If you're at the equator or near the equator, the sun is much more direct. Okay, and it's focused, the sun is focused on a smaller area than if you're up at higher latitudes where that sun is spread out over a greater distance. So, you can see this distance here is larger than this one down here. All right. And what that means is when this energy is spread out over a larger area, the heating rate from the sun is lower than it is over here where the sun is more direct. And the upshot is that the tropics are heated more efficiently by the sun than the poles are. Okay? And this doesn't matter whether it's Earth or any other planet. Okay? Wherever the sun is shining more directly, you're going to have more heating. Now at the same time, the Earth is, or any other planet, is radiating its energy out to space in infrared energy. Okay? And it's trying to cool the planet. And it's the difference between those, so the sun coming in and the infrared energy going out, that determines whether or not the location you're at, the latitude you're at, is heating or cooling on average. Not surprisingly, you get net warming in the tropics and net cooling when you go to higher latitudes. Okay? And if you don't believe me, here's some observations. This is from Earth, this is from a satellite, and it's looking at the net difference in radiation of the amount coming in and the amount going out. And this is for January on the Earth and July. And these hot colors down here indicate positive input of energy in watts per square meter. You can see it's about 150, so we're talking about a light bulb's worth spread over, a meter square, whatever that is. Right? Down in the tropics. And then in the poles, you're actually negative. You're losing about a light bulb's worth of energy per square meter. Right? Now, if nothing else was happening, the tropics would get warmer and warmer, and the poles would get colder and colder because the tropics are gaining energy and the poles are losing energy, and off you go. We clearly know that doesn't happen. I mean, the tropics are warm and the poles are cold, but they don't keep going and getting warmer and warmer and colder. So there must be something going on, and in fact there is. It's the atmosphere, and in the case of the Earth, which has an ocean, that heat, that excess energy, that excess heat in the tropics is being transported towards the poles. Okay? And that's what keeps the planet in its relative thermal equilibrium. Now let's jump to Mars for a minute. This is a map of, it's an animation of data taken from orbit again, of Mars's daytime surface temperature over the course of a few years, a few Mars years. And it basically, as you can see, it behaves kind of like the Earth does. Right? It's warmest here in the tropics, and it moves up and down with the seasons. And that's because Mars is tilted almost the same angle as Earth. So it has seasons just like Earth does. Right? Winters, summers, okay? And you can see that as it, as it loops through. And so the effect is just like Earth, which is that in general, Mars is receiving more energy at its tropics than it is at the poles. Right? And just like Earth, there must be something to maintain that, otherwise the tropics would get warmer and warmer and the poles would get colder and colder. Right? Well, back in 1735, so just a little bit ago, this guy named George Hadley realized there must be something going on, and he proposed a circulation that we now call the Hadley Cell, named after him, that would accomplish this transport. Now, he didn't actually think about the transport. He was trying to explain the trade winds. But it turned out to be coupled. It's really the same problem. And what he said is, there's winds that blow down from the poles toward the equator, and then they rise because they're hot, effectively just like a hot air balloon would rise. And then aloft, they move back towards the pole, and it generates this circulation, the cell that moves this excess heat around and keeps the planet from getting too hot at the tropics and too cold at the poles. Okay. Well, since 1735, we've learned a little bit more. Okay. And on the left, I've got Earth. It turns out Earth doesn't have just a Hadley cell, one single cell. In each hemisphere, it actually has 3 cells. It has the traditional Hadley cell, and these 2 other cells called the Ferrel cell and the polar cell. I want to focus on the Hadley cell. But the basic idea is the same. Right? Air rises from the tropics, moves poleward. The cold air from the poles moves equatorward. Right? And try to keep the planet balanced that way. Now, Mars is a smaller planet than Earth, and it rotates about the same way, but it's smaller. And without going into the details, what that means is Mars does not have 3 cells. It has one big dominant Hadley cell in each hemisphere and a very small secondary cell up near the poles. This is shown at equinox, so the sun is shining most intensely on the equator at this point. So think of Mars as basically just having one big Hadley cell in each hemisphere, rising at the equator, more or less sinking at the poles. This is at equinox, like I said. Now, at the solstice, which is actually more common, the solstice is, for example, in winter or summer, and the sun, in this case, is shining closer in its southern summer, northern winter. So the air rises actually in the southern hemisphere, goes up, crosses the equator, and sinks down near the North Pole, and it switches at the other season. So Mars has just very much one big Hadley cell, as opposed to Earth that has all these other 3. Okay? Okay, so the Hadley cell of Mars, except for a few locations on the surface of Mars, we have never measured the winds on Mars, the circulation of Mars. You go back to the Viking landers, that's 2, Viking lander 1 and 2. Pathfinder, in the 90s, it was a short-lived, few months experiment. And most recently, the Phoenix lander up in the poles had a wind sensor of sorts. It was basically a stick with a string tied to it, and we watched the way the string moved, and right? Not highly sophisticated, okay? That is it for direct measurements of the atmosphere circulation of Mars, okay? So, effectively, we've never directly observed the circulation of Mars. But we can infer from temperature, subject to a bunch of assumptions, what the winds are actually doing. Okay? And we also have climate models. And they can tell us what we think the circulation should be. And in fact, they show that there is this extensive Hadley Cell circulation. Okay? And we also have indirect observations of temperature and dust and clouds and other things that don't measure the circulation directly, but they certainly have to be consistent with what we think the circulation should be. Right? So we can use those observations to test the models and to test this idea of the Hadley Cell and the circulations, even though we don't have direct wind measurements. So let's take a look at some of those. On the left side are observations obtained from the Mars Global Surveyor Orbiter at Mars, the thermal emission spectrometer data. And on the right side is a model. Okay, and let's just focus on the top panel here, the top row. Okay, this is temperature as a function of height and latitude. This is the South Pole on this side, on the left, and the North Pole on the right. South Pole on the left, North Pole on the right, and up in altitude. And so just by looking at the temperatures, you can see that it's Southern Hemisphere summer. It's nice and warm down in the Southern Hemisphere. It's very cold out in the poles in the north. Okay, and then we can look at the model. And hey, it looks not too bad, right? I mean, it's generally the right idea. You can see there's a strong gradient in temperature. It's pretty warm here and goes rapidly cold. Strong gradient here, goes rapidly cold. So the basic structure is there. The model seems to be reproducing the observations of temperature reasonably well. Not too bad. All right, and then down below are the winds. These are the winds blowing in the east-west direction, the so-called zonal winds. These are showing you where the jets are. And as I said, from the temperature measurements, we can make some assumptions and actually calculate what we think the wind ought to be. And that's what's done here. You notice there's no data here in the middle, out in the equator. And that's because the assumptions that we make to derive those winds are not valid at the equator. So we don't know what's going on there. Okay? But what you'll see is that over in the north, there's a strong westerly jet. This is a jet stream. Okay? The model has that as well. Okay? Both these red spots. And in the other hemisphere out in the south, there's some easterly winds there. And overall, the model seems to do a reasonably good job. So from that, we can say, well, it seems to be getting the bulk characteristics of the observations. And so, you know, maybe the model can tell us something about the circulation. And indeed, what the model predicts is that there is, in fact, this big overturning circulation called the Hadley Cell, which we cannot directly observe. Okay. There's other stuff too. Okay? We can look at where there are water ice clouds and where there's water vapor. This is from the same instrument that I showed for those animations of temperatures at the surface. This is water ice clouds. Now we're at a function of latitude from the South Pole to the North Pole. South Pole to the North Pole up here. And as a function of time. There's several Mars years plotted here. And you see this looks fairly periodic. Every so often there's a big blob of clouds that appears in the tropics. Okay. And down below is the actual water vapor, the amount of water in the air. Not ice clouds, but actual water vapor. And you can see that there's a big blob occasionally in the northern hemisphere up by the North Pole. And over time, that water seems to get pulled off towards the equator. Right? So over time, it moves equatorward. Okay. The fact that this cloud appears here is a direct consequence of the water moving from the poles to the tropics, where it then gets caught in the rising branch of the Hadley Cell and, at least partly, goes up and produces these clouds, more or less at the same time every year. Very repeatable. This picture of Mars, you can actually see these clouds here, sort of whitish. They're faint, they're very diffuse. They're not like these typically big, thick clouds that we see on Earth. But there's more cloudiness here in the tropics than there is down in the higher latitudes. And you can see the Mars polar cap up here in the north, which has a lot of water ice in it, which is the source of the water itself. Okay. In the last few years, we've got data coming in from a new instrument called the Mars Climate Sounder that's on a new orbiter. And it's providing a lot of really interesting information. And one of the advantages to this instrument is that it doesn't look just down at Mars, straight down. Okay? But it actually looks down and off to the side in an oblique angle. And when it looks at that oblique angle, it actually samples different layers of the atmosphere. So instead of just telling us how much stuff there is in a column, we can actually start to get now at what's the structure of that stuff in the vertical as well. Okay. And here's what it saw with respect to dust. This is a plot of height versus latitude of the amount of dust you have. This is at 2 different seasons, different times of the year. And what you find, not just at these seasons, but if you look at all the seasons from this instrument, you find that there's this big blob of dust sitting up in the middle of the atmosphere. There's a maximum of dust aloft. This was very, very surprising, somewhat anyways. Compare that to what we usually had assumed the distribution of dust was, which was its maximum near the surface, because after all, dust comes from the surface, right? So it gets lifted near the surface and it mixes its way up and slowly dissipates with height. This is what we've assumed for decades. And what we saw was that's not the case at all, right? There's a bunch of dust up in the middle of the atmosphere, which seems pretty strange since dust comes from the surface. And in fact, in the paper McLeese et al. 2010 basically said, what's going on here? This doesn't fit our current understanding of the way that dust behaves in the atmosphere of Mars. We don't understand where this is coming from. Well, we shouldn't have been so surprised because, in fact, we've also known for decades that there are elevated layers of dust. We've seen them. Right? Remember the Mars rover Opportunity? Sits right about here, actually. This is an image looking out at the limb. So you're looking through the very thin envelope of atmosphere and down below is the surface. But you can see these layers. They're clearly layers right here running up and down, right? They're there. It's pretty obvious. Right? Here's another image. Hey, what's this little thing sticking up out of the atmosphere? Right? There's stuff up there. Okay. And in fact, you can go back, Clancy et al. 2010 said, layers of altitude increasing dust increasing as you go up in altitude. And you can go all the way back to the Viking orbiter area, Anderson-Leovy, 1978, that showed there are these elevated layers of dust and aerosols. So they're there. Okay. It's just now we're quantitatively measuring them really for the first time, and they've come back to light, perhaps, as to how persistent they are and how widespread they are. Okay, but here we have a paradox. Right? The push me, pull you, so to speak. On one hand, we have a Hadley cell that's required to maintain this energy balance. It has to be there, otherwise the tropics get too hot, the poles get too cold, and everything gets out of whack. On the other hand, the Hadley cell can't produce the observations of the dust that we're seeing. So if you want the Hadley cell to keep the energy balance correct, you have to throw out the dust. But we've observed the dust. You can't get rid of the dust. It's there. So if you want to keep the dust, you've got to get rid of the Hadley cell, because the Hadley cell can't produce the dust. Paradox, right? All right. Well, I haven't told you why the dust distribution that we're observing is incompatible with the Hadley cell, so let me do that now. And it's really quite simple. If you start with dust near the surface, which I think is indisputable, because the surface is the source of the dust. So we have dust devils and other things that lift the dust up and put it into the lower levels of the atmosphere. That's pretty clear. And then you apply a Hadley cell, which is this wind in the vertical that's blowing stuff upwards. Okay? And you allow that to operate. What you would get is this, which is exactly what we've assumed for decades. The dust would be mixed upwards and it would decrease with height as you go. Okay? What you can't produce with the Hadley cell is this. You can't start with dust down here, mix it upwards, have nothing in the middle, and then suddenly have stuff appear aloft. It just doesn't work. Okay? Okay, so let's go back to the great blue orb, our home planet of Earth. Because it turns out that there's a very similar paradox to Earth that was figured out about 50 years ago. This is a plot of what we call equivalent potential temperature, which is a lot of words, but think of it just as energy. It's the amount of energy in the atmosphere, okay? And this is taken in the so-called rising branch of the Hadley cell in the tropics of Earth, and you can see there's a bunch of energy down here, and then there's not much here, and then there's a big bunch of it up here. So this is a profile that looks similar to the dust, right? Stuff down here, and it's an elevated layer of energy. And it's got a similar problem, which is the Hadley cell can't possibly produce this. If you start with the energy down here and you try to move this energy up, you cannot produce that profile. So we have the same question. How does the energy down here, or how does the dust down here, make its way up to here and have a minimum in the middle? Okay. And as I said, well, the Earth meteorologist figured this out about 50 years ago. And here's the paper, 1958, Real and Malkus introduced the concept of hot towers. What are hot towers? You're looking at one. They're just thunderstorms. It's a picture of a thunderstorm. Okay. And here's how they work. Thunderstorms take stuff down here near the surface in the so-called boundary layer, and they transport it rapidly, almost in an undiluted manner. Whatever you have down here goes up, and they spit it out aloft. Right? And in the rest of the atmosphere, which is most of it, the air is actually sinking. Okay? And so if you average this scenario, you get a lot of stuff down here, you get a lot of stuff down here, and on average, there's not much in the middle except for this little narrow spot where the thunderstorm is. And hundreds and hundreds and hundreds of other kilometers where there's no thunderstorm at all. Okay? This was the resolution to the paradox. In a more general sense, let me show you this schematic. Okay? Let's start on the left side here. Suppose we start with an initial distribution of stuff. This can be dust, this could be energy, it could be dust bunnies, doesn't matter. Okay? And we've got stuff down near the surface, and so it has a profile where you got a lot of stuff down here, then it drops off and goes to near zero aloft. That's what we're going to start with. And let's try to move this stuff in two different ways. Let's try to move it in the middle panel here in a diffusive way, in a mixing way, in sort of a Hadley cell way. And if you do that, and you gradually mix this stuff up, you would get a profile that looks exactly like this. It decreases with height. Right? Most of your stuff's near the surface, and it moves upwards. And then let's look at a process called non-local deep transport. This is like the thunderstorms. What you do is you take the stuff down here and you send it up rapidly through these cores and spit it out at the top. And the rest of the atmosphere is sinking and it's not transporting this stuff at all. And if you look at the profile there, you get something that looks like this. A lot of stuff down below. A lot of stuff down below here. Stuff at the top and a little bit on average in the middle, but not much. Okay. So this is a way of producing an elevated layer of stuff, like we observe on Earth for energy, like we observe on Mars for dust. The non-local part means that the transport is occurring over a great distance. So the stuff up here is coming from stuff all the way down here. It's not a local transport. This in the middle is a local transport. The amount of stuff you have at one altitude depends on the stuff immediately below it, and it comes from just below, locally. So it's a non-local transport, moving stuff over distance from one location to another. And when we look at Earth, the tropical rising branch of the Hadley cell is just a mean circulation. It's not the actual circulation. The actual circulation are the rapid rising motion over a narrow region in the clouds and widespread subsidence of the air. In the mean, if you average this out over the tropics, you get mean rising motion. In other words, it's the slight difference between the upward motion and the downward motion. So the narrow but intense thunderstorm updrafts plus the widespread subsidence is what gives you the mean rising branch of the Hadley cell. The transport, however, of energy and other stuff is accomplished through the storms, not by the Hadley cell, which is just a mathematical construct. Okay. Now this is important. So the Hadley cell in the mean, in the mathematical sense, is still there. And that's what gives us that required movement of energy. But the Hadley cell itself is not what's actually moving the energy. What's moving the energy are the thunderstorms and the compensating substance. Okay. Now, back to Mars. Now we've got Earth out of the way. Okay. There's two major issues now to resolve for Mars. One is, how is the dust transported so high into the atmosphere? We've got dust in the boundary layer, but how does it, that's a few kilometers, 5 kilometers. How does it get up to 30 kilometers or 40 kilometers? Okay? And is there non-local deep transport occurring on Mars? Okay, so let's start from the beginning. Dust in the boundary layer. We know how dust gets into the atmosphere of Mars. We've observed it. This is an image taken from the Mars rover Spirit at Gusev Crater on the top. And it's a series of still images that are put into a loop here. And you can see dust devils moving across the surface. And this is one way dust gets in the atmosphere of Mars. It's a dusty place, and stuff spits dust in the air all the time. There's also little windstorms and little dust storms like I showed you on the title slide that are constantly putting dust into the lower atmosphere of Mars. And this is actually taken from orbit, believe it or not, looking down on the same spot at 2 different times. And if you look closely, as it flashes back and forth, you'll see these little dots of things come and go. Okay? These are dust devils, big ones, like tornado size. We don't get them that big on Earth. But on Mars, they can get that big, and they lift dust. But again, even at best, these things may only be 10 kilometers deep. Okay? So a dust devil is not going to take dust from the surface and put it at 40 kilometers, because there's no 40-kilometer tall dust devils on Mars as far as we know. Okay? So we have a way of making the boundary layer dusty. That's the source of dust for the atmosphere. It comes directly off the surface, and it gets stuck into this boundary layer. Okay. After that, we really have to start moving to models again, because we just don't have really the observations to look at the details of this. So one of the things that I do, in fact, I spend most of my time doing, is actually modeling the atmosphere of Mars. But instead of using climate models, I use what are called regional scale models. So rather than looking at the whole planet, I focus on specific regions and try to understand the details of the circulation that's going on at those smaller scales. Okay. And one of the places we looked at were the Tharsis Montes, mountains of Mars, on the Tharsis Plateau, which have these enormous dormant shield volcanoes. And you can see them, one of them sticking up right here. They're enormous, like 20 kilometers high. Okay, so 3 times, 4 times the size of Mount Everest. Right? Big. And what happens when you stick one of these things in a model, which presumably represents the atmosphere of Mars, and you shine the sun on it, is that it heats up at the surface, and it produces an upslope flow. And we see this on Earth all the time. Right? Upslope, downslope, sea breezes, same kind of stuff, right? Stuff comes and goes. Well, when you heat these things, the air flows from out on the plateau and up the mountain and keeps going many kilometers, tens of kilometers above, until it finally spits out at the top. Okay? And in fact, so it looks something like this. This is the circulation that you see. Takes stuff from down here, goes up, spits it out. Now, we also happen to have dust in this model, and that you can see in the brown. So you see the dusty boundary layer down below. You can actually see the dust down here. All right? And it goes up and gets spit out, and lo and behold, there's a bunch of dust at altitude. And in between, there's a not-so-dusty place. So this is a non-local deep transport mechanism. Okay? So rapid transport through a narrow updraft core of dust. There's a maximum of dust concentration aloft and a minimum at about 10 kilometers. Okay? And it turns out it also works for water. So a few years later, we put some water in the model because we were interested in looking at the clouds associated with these things. And sure enough, it doesn't show up so well here, but if you, can everybody see the green shading here, the light green shading? That's the water. I don't know, maybe we can dim the lights a little bit, but it might help a little bit. And it basically does the same thing. You got water down in the boundary layer, which presumably actually originated from the North Polar Cap, as I showed you before. So this water is coming down, right? And then it makes its way into circulation. Up it goes and out and produces this elevated layer of water. And not surprisingly, aloft, you also can get these clouds, which have a diurnal component. So in the late evening, you actually tend to get more clouds. And there's Dave here. Yeah, Dave Hinson back here. He's worked on this a little bit and has shown that the cooling that helps produce this cloud is associated with the thermal tides and other type of disturbances on Mars. So there's a diurnal signature to it as well. But the point is, you got to get the water up there first. Okay. So how do you get the water up there? Through this mechanism. And it doesn't just work on these big, enormous volcanoes either. Good, thanks. This was a simulation that we did looking at the hazard assessment for the Mars exploration rovers. One of the places that the rovers were going to go to were Terra Meridiani. This is where Opportunity went. a big flat plain on Mars. It's the flattest place on Mars you can imagine. It's flatter than the Great Plains of the US. You look out on the horizon and see for miles and miles and miles and see nothing but horizon. The exception is, of course, every once in a while, there are these little impact craters, okay? And so when you find these little impact craters, look what happens. All of a sudden, boom, boom, you get these circulations. Same thing. Everywhere there's a little bump, crater rim, valley, whatever it is, they produce these upslope circulations that pump and move stuff upwards. This is a much smaller scale. These are 20, 30, 40 kilometers in scale instead of these big volcanoes. Here's another one from a crater rim. This is actually some simulations we're doing for the Mars Science Laboratory, which is the next rover that will launch around Thanksgiving. Okay. Same sort of thing. Here's the topography along the bottom. It's kind of bumpy. And whoa, look at this. This big updraft, meters per second, 6 meters per second up, going way up in the atmosphere. Now, what's shaded in blue here, if you can see this, is actually sort of a representation of where the boundary layer is. So you can see here, the boundary layer is only about that deep. It's a few kilometers. And it's like that most of the way until you get here and bang, shoots it way up, kilometers and kilometers above the boundary layer. And it takes the dust and sucks it in and blows it out the top, which is what's shown here in the black contours. So it's taking the dust in and spitting it out aloft. Yet one more example. This is a cross-section through Valles Marineris Canyon. This is what we believe to be the largest canyon in the solar system. Okay. It's about as long as the United States. Okay. It's quite a bit wider. You couldn't see from one end to the other if you were there, but it's enormously deep, very, very steep. It's 8 kilometers deep. Okay. And not surprisingly, it does sort of the same thing, which is that, you know, the sides of the canyon heat up, the air goes up, spits out at the top, and everywhere else the air is subsiding downwards. Okay. So it would do the same sort of thing. And finally, it's not just circulations associated with topography, but as I mentioned, there's local dust storms. Here's a simulation of a dust storm that we just recently completed in the last year. Same sort of thing as the plot I showed a couple slides ago. This blue stuff indicates where the boundary layer is. So you can see it's, you know, it's pretty deep, 6 maybe kilometers or so, right? And then we have this dust disturbance right smack in the middle, these strong updrafts that penetrate well above the boundary layer and spit this dust out above the boundary layer. So it transports it out of the boundary layer and into the atmosphere. This is the same simulation, and what I've done on the right side here is just done a 3D rendering of what this sort of might look like. This is a surface of constant dust. And the idea is that it illustrates, you can see this rising column of dust in these two cores here, and at the top it starts to spread out. Okay, so the models seem to indicate wherever we look, wherever we model, we see this sort of transport going on all over the place at a whole variety of scales. Everything from sort of the smallest craters up to these giant Tharsis volcanoes. Okay. And as I said, we can't observe the circulations directly. We just don't have those observations. But there are indirect things. And one I think that is really compelling is a paper that was put out by Martian et al. In Icarus, 2009, a few years back. And they looked at data from an Omega instrument, which looks down looks down from space towards Mars. And they did something very interesting. They saw this little dust disturbance, and they actually went back in their data and they looked at that same location prior to the dust disturbance. So they had sort of a before and after picture, like you see on those cheesy television commercials, right? You know, this is what you look like before, and this is what you look like with dust. Okay, and the key is, though, with the before picture, they knew sort of how the surface appeared, how the generic atmosphere appeared, and they could subtract that from the after picture and see what the perturbation was, okay? And when you do that, you get this image. It's about 20 kilometers. This is the scale here, so it's not very big, okay? And what you see, all of a sudden, popping out in the atmosphere is amazing fine-scale structure of dust. It's very, very dusty in just a few little spots that can be maybe just a few kilometers to maybe up to 10 kilometers. Okay? And there's also regions where it's very, very clear. Okay? So there's a lot of structure there. And what they thought is that these are actually dust plumes, kind of like the ones that we've been modeling. Okay. Are they? I don't know. But they're at least consistent with the modeling. Okay? Okay, so let's put all this together now. We think, or we thought, depending on which side of the fence you're sitting on, that Mars has a Hadley cell like this, where air rises in the tropics, goes up, and sinks out near the poles, and does this sort of thing. And what I'd like to suggest is that instead of this, okay, so get rid of that, let's think this. Very, very different. And the idea here is that rather than this slow overturning circulation, what we in fact have are very dynamic, very active circulations that are local, pumping stuff up, spitting it out aloft at various levels. Okay? And in between, there's subsidence, air sinking in between. Okay? And shown dashed in this dashed red line is sort of the height, notional height of the boundary layer. So it's taking stuff out of the boundary layer, putting it up aloft. Okay? And these circulations can be asymmetric. So for example, if you look at this big one right in the middle, the air blowing out here in this direction can be more than this way. Okay? The air out here can be more blowing faster out this way than that way. Right? And if you take this and you sort of average it all together, it produces exactly the same mean circulation as the Hadley cell. Okay? So in other words, we still have a Hadley cell in a mathematical sense. You still have this overturning. Okay? The air is rising here more than it's sinking, and the air is sinking here more than it's rising. You can still have rising air where it's sinking, and you can still have sinking air where it's rising. You just have to have it in the right balance. Okay? And likewise, although in the mean you want the air moving from left to right aloft, you can still have that even if there's places where it's going in the other direction. It's the mean that matters. As you can imagine, though, the transport is very, very different. There's a big difference between moving stuff in a big, slow circulation versus having it go up in a matter of hours up into the upper atmosphere and getting blown around that way. Right? And we see that in the observations because, again, you can't produce easily anyways and in the obvious way the dust distribution that we observe with the Hadley cell. It's got to be something else, and this is consistent with that. Okay, so let's compare it then. In the old version of Mars, we have this rising region near the equator where it's warm and the air is rising, and sinking air out near the poles, and at the surface the air flows out there in sort of this slow overturning circulation. What I'm proposing is that Mars actually looks something a lot more like this. There are very localized, patchy regions of air going up and down all over the planet. Okay. They are more concentrated, or there's a net upward flow near the equator and a net downward flow at the poles. So it gives you the same answer in the mean. And the mean flow is still at the surface anyways from the poles towards the equator. But there's more. Okay. In 2006, we showed that there's a large fraction of vertical transport in the rising branch of the Hadley cell that's accomplished in very regional areas. And here's, for example, some simulations from one of these global models. You're looking down on the whole planet, North Pole up here, South Pole, the equator running through the middle. Okay? North Pole up here, South Pole, equator in the middle. And you're looking down and you're looking, where is the air going up and down? Where it's going up, I've colored in red. Where it's going down, it's colored in blue. And you can see, first of all, that it doesn't look anything like a sort of Hadley cell. It's very spotty, it's very patchy. There's regions where it's intensely going up, right next to regions where it's intensely going down. And if you go and then look a little higher up in the atmosphere and look where the dust is, you see a similar thing. There's sort of blobs where it's dusty and blobs where it's not. And so it turns out that the circulation in the mean doesn't really exist at the surface either. And in fact, we know this. Back in 1994, there was a paper that looked at so-called gyres and boundary currents in the surface flows of Mars. Let me give you an example. This is output at the surface from the Oxford Mars general circulation model. Predicts what the winds are doing at the surface. So again, here's the North Pole up here, South Pole, equator in the middle. And you can just look at the winds and you can see some patterns. Okay. And I've helped you out a little bit. Draw some arrows on here. Here's what's sort of going on at the surface. There's places where the air is flowing from the pole towards the equators, like we would expect in a Hadley cell. But then there's also clearly places where it's going exactly the opposite. Persistently. So what we have are transport corridors. We have places where stuff can easily move from north to south, and places where just the opposite is occurring. And we've actually observed this. Okay. Wang et al., 2005, looked at how certain dust disturbances in the north move dust from north to south. And they found under certain conditions that this dust, which may be hard to see here, but maybe you can see it, it moves from up here in north and manages to make its way across the equator to the south. But it only does it in certain corridors. So these corridors, these transport corridors, have really been observed. Okay, we know they exist. Now, I'm going to jump back to Earth again, because it seems to be doing a pretty good job at an analog. Because it turns out these boundary currents, this local rising motion, is analogous, once again, to the way the Earth behaves. And it's analogous to what we call the rising motion over the Pacific warm pool. The Pacific warm pool is a blob of warm water that sits out here just north of Australia. And in fact, this is where the air is rising dominantly in the Hadley cell in the mean sense. This is where all the bulk of the thunderstorms are. The air is not rising in thunderstorms uniformly along the equator. The air is rising along the equator in thunderstorms here and a few other spots, but locally. And this sets up yet another circulation called the Walker circulation. So we've got the Hadley cell in the mean that goes from the equator towards the pole. We now have another circulation that starts at the equator and doesn't move in latitude, but moves in longitude. It goes up over Australia and moves across the Pacific and sinks over at South America. So two competing circulations, one going this way in latitude, another one going this way in longitude. Okay. And if we look at the surface pattern, wind patterns of Earth, we also see that, less so than Mars, but there's a lot of variability in the winds. Okay. So things are not uniform in latitude or longitude on Earth, nor are they on Mars. Okay, so let's modify this hypothesis a little bit. So here's the old one. Here, we had the intermediate one. Now what I'm suggesting is that it's not just that we have upward and downward motion, it's actually focused in specific regions. So yes, there's more upward motion than downward motion at the equator, but more than that, the upward motion is focused at specific longitudes. Okay. And there's a surface circulation pattern that must be there to achieve this. In the mean, we get exactly this. We get what's on the left. In reality, though, this is what's actually going on. At least that's my hypothesis. So what are the implications for this? Well, on Earth, non-local deep transport, particularly by thunderstorms, is crucial to an accurate representation of climate, of the dynamics of the atmosphere, of the chemistry, and of the hydrologic cycle, among other things. If you don't have this transport by thunderstorms, you don't get the climate right. You don't get the winds right. You don't get the storms right. It doesn't rain in the right place. The chemistry's messed up. All kinds of stuff. It looks good in the bulk. You look, oh yeah, it looks like Earth. Yeah, it's warm at the tropics, cold at the poles. Oh, look, there's a mean Hadley cell. Oh, there's a storm system that goes by. You see all those things, but when you focus in on them, and after all, we're after the details. We want to know what's really going on. It doesn't work. It's wrong. You have to include convection, deep thunderstorm convection in climate models, or you get it wrong. So is this the case for Mars? Well, I think it is, and I think the Mars dust cycle tells us that that's the case. Okay. The thermal circulations that I've been showing you associated, these non-local deep transport associated with the topography, are an important and necessary component of the dust cycle that help to maintain the global dust opacity. I'm proposing these are the things that help move the dust out of the boundary layer and get it up into the atmosphere where we observe it. Not only that, but it gets it in the right place. Okay. If we don't have those, okay, we don't get the right dust. And also there's a contribution from some of these local dust storms that I showed you. Okay. Now on Mars, what's really important about dust is that it's a first order radiative forcing. Dust really matters in Mars. If you didn't have dust in the atmosphere of Mars, you would get a very different Mars climate. Dust absorbs solar energy very strongly, and it also radiates. So it's intricately tied to the thermal structure of Mars, and as I showed, the thermal structure also implies a certain wind field. So don't get the dust right, you don't get the temperature right, you don't get the temperature right, you don't get the winds right, and everything falls apart. Okay? So it's really important to have the dust correct, because that determines the temperature, and the temperature drives the circulation. Okay? So if we don't have the Mars dust cycle right, we don't got it right. We have to have a mechanism to get the dust in the right place, and the Hadley cell alone can't do it. So just, again, this is sort of how things are probably operating, at least I'm proposing that they operate. We have big volcanoes injecting dust way up. We have little craters and hills and valleys and other things doing the same thing at smaller scales. We have occasional dust storms. And they take the dust out of the boundary layer sitting down here, and they pump it up to higher altitudes to produce these elevated layers of dust, to produce the mean circulation that's consistent with the Hadley cell. Whatever happens with dust, there's nothing special about dust. It should happen with water and anything else you stick down there. Methane's been a big talk on Mars. If methane's going to move around like this too, that's going to have a big implication. Okay. Talk about the hydrologic cycle for Mars. Clouds, okay? These are Hubble Space Telescope images. This is sort of real color. This is in an ultraviolet band because it happens to accentuate where the clouds are. So you can really see the clouds. This is that aphelion cloud belt. You notice it's more cloudy in the tropics here, especially over the volcanoes here. Okay. So water comes off the cap in the spring when the sun shines on the cap and the water starts to sublimate off the cap. And presumably it starts to move in this Hadley cell sense down towards the equator, where it gets caught in the uprising branch of the Hadley cell and rises up to produce the clouds, right? Maybe. What I'm proposing again is that this water transport is longitudinally asymmetric. So it doesn't just flow off the cap. It has to make its way to those transport corridors. And only then can it get to the tropics. And then once it's in the tropics, it then has to make its way to the preferential regions of rising motion. So the clouds that we see here I'm proposing don't come from just a movement of water from the poles to the equator and then rising everywhere along the equator. No. All the water up here has come through very narrow corridors and risen through very narrow localized regions. Eventually it spreads over the whole tropics through the jet stream. Okay? But it doesn't just all get there and then rise uniformly. This also has importance for how water interacts with the surface. This is an image from the Viking Lander 2. This is water frost sitting on the surface of Mars. It gets cold enough, you get frost, just like you do on your windshield, even in the Bay Area every now and then. Okay? Water is exchanged with the surface. And the amount of exchange depends on the relative humidity. If the air is already saturated, for example, this frost is going to sit there. It's not going to sublimate. There's nowhere for it to go. Okay? If the air is very dry, you're going to tend to sublimate this ice away very quickly. A longitudinal asymmetry of the circulation would result in preferential exchange regions. Places where there's a corridor of water are going to have water flowing over the surface, water vapor flowing over the surface, okay, in the atmosphere, that can exchange with the regolith. Other places are going to be relatively dry. They can actually suck water vapor out of the surface. So it's going to be an exchange that depends on the circulation. So for Mars hydrology, what we have is something like this. Water comes off the cap, must go through these corridors where it rises, ultimately being distributed around the planet. There's also flows going back in the opposite direction, opposite the Hadley cell, that take relatively dry tropical air and move it back over the cold poles, which are moist. And there's also regions here and there where the air is actually sinking. So that's the story I'd like to tell. But I think it's important to point out that there could be other possibilities. One that I've heard informally is that, well, maybe it's not non-local deep transport. Maybe it's clouds. Maybe clouds are doing this in some way. And here's the explanation for that. And then I'm going to tell you why I don't think that's the case. If we assume an initial dust distribution like this, which is what we've always assumed, and we stick a cloud in there, somewhere along here, what's really going on? Well, what's really happened is that the cloud is formed by condensing water onto the dust itself. The dust is a nucleation center for the cloud. Okay? And these particles will grow, like cloud particles do, and they'll eventually settle out. And as they settle out, they carry the dust with them. So it's a way to remove dust from that layer. So if you wait a little bit, you get something that looks like this. Suddenly you got a hole where the dust was. The cloud was, it scavenged the dust, and out it came. Okay. All right, so in a broad sense, you have dust down here, a minimum, and you have this elevated dust layer. Okay, could be. The problem, though, there's two problems, actually. First of all, how does the dust get there in the first place, along with the water vapor? In other words, in order to form this cloud, you have to have the dust and the water there to begin with. And the dust and the clouds don't explain how they got at 20 or 30 kilometers above the surface to begin with. So you got to get them there first of all, before you can even invoke this. Okay. So that doesn't solve that problem at all. The clouds don't solve that problem at all. And the second thing is that the clouds also trap dust and limit the further vertical movement of dust and water. So, if you have a cloud here, nothing can get through it. So you can't get more dust and stuff up here once the cloud is there to begin with. Okay. From this, I conclude anyways that clouds are unlikely to be primarily responsible for the observed vertical dust structure. Now, I want to be careful here. I'm not saying that clouds are not important. I think they are hugely important. Okay. What I'm saying is I don't think they're the primary mechanism by which this is produced. Clouds will absolutely, undoubtedly perturb the dust and water structure. But they cannot be primarily responsible for the observations we see. It just doesn't seem to fit. Okay, so good timing. I'm just going to summarize the stuff I went through today, and then if there's time, I'd be happy to take some questions. First of all, we have observations of dust that show a vertical distribution that is incompatible with transport from a Hadley cell. So we have to revise our thoughts on the Hadley cell in some way. If we look back at Earth, and we also do modeling studies of Mars, and what limited observations we do have, they strongly suggest that the distribution we do observe is a result of non-local deep transport. So it's consistent with all of these things. It's not proof, it's consistent. Okay? The Hadley cell, we have to remember, got both high rise, is a mathematical construct. It's not a real circulation. If you go around in Mars or Earth with your Hadley cell meter trying to detect a Hadley cell, you're never going to find it. You will find either rising motion over narrow regions occasionally, or more likely you'll just find sinking motion exactly where you think the air should be going up. Okay? It's the sum of that strong upward motion and the downward widespread sinking subsequent motion that makes the Hadley cell. Okay? The implication is that the transport of dust, water, other quantities, energy, methane, whatever you want to stick there, is accomplished through the real circulations, not through the Hadley cell itself. Climate models with coarse resolution will not be able to resolve the full range of non-local deep transport circulations. So again, we can look back to Earth. Earth has climate models. They have to parameterize, which is the next step here, these circulations. They have to parameterize thunderstorms. If you don't have them in there, you will still get something that looks in the bulk like Earth's climate. And at first glance, you say, oh, no problem. Looks good. Okay? Then you look at the details and you realize it's all wrong. Well, we're in a similar situation now for Mars. We have these models that are not parameterizing these processes. They're not in the models. And we look at it and we go, oh, not bad. I showed you those pictures. Oh, temperatures look about right. You know, things seem to be okay. Then you look at the details. And there's all kinds of problems. Well, the model isn't quite, it's too warm here, it's too cold here, the dust isn't quite moving around right, we can't explain the water cycle, we have to set some parameters to some funny values in order to make things work properly. Okay? So, and I'm not saying that this is entirely all the result of non-local deep transport, but the fact of the matter is we already know from Earth that if we don't put the stuff in there, we don't get the right answer. And so what I'm going to suggest is that non-local deep transport may be, in fact, quite important for Mars. It may be the dominant process by which things are actually moved around. And therefore, we need to include it in climate models. Okay. And I conclude my talk on that point. Thank you.
Scott, if I could kick it off with the first question. So it seems like we can get the first clue about where non-local deep transport is going to happen from the topography, but there's going to be other factors, aren't there? Like, well, I'm thinking of things like distribution of dust and heating from the changing albedo on the surface or something like that. Do you have any thoughts on how we're going to do this parameterization?
Yeah. Yeah, I actually have thought about it a little bit, but your point is well taken, which is it's actually a very complicated process, and we know this even without non-local deep transport. We know this from trying to even understand the dust cycle on Mars without the complicating factor of non-local deep transport. Obviously, it matters where the dust is. If you have a surface where dust is not easily lifted, you're not going to get dust, right? And in fact, we don't really know very well on Mars where its dust is easily lifted and where it isn't. So there's a problem there already. What's the source of the dust at the surface? And what we do have an idea, though, is albedo and the thermal properties of the surface. So at least we have somewhat of an idea of how it heats and cools. But even that we know changes with time depending on where the dust moves. So it's all coupled together. And now we want to throw in this idea of non-local detransport. And I think the idea I have in my mind is that given a certain albedo, thermal inertia, and dust abundance, that one can look at the topography and at least begin to estimate the effect that these circulations would have. Now, this requires that you know these other input parameters, right? But that's no different than where we are now anyways, right? So we can take the information we have, and maybe if we start plugging this into a full dust cycle simulation, all the stuff will start to come together. But
I guess I missed it. Why don't you call it local deep transport rather than non-local deep transport? I missed that.
Okay. So the non-local part means that the place where it's coming from to where it's going to are separated by some large distance. So it becomes non-local. And that's as opposed to the idea of mixing things in a turbulent or diffusive way, where the amount of stuff that you have here depends on exactly the amount of stuff you have just below it or above it.
But it is local in terms of a spatial expanse of the surface.
That's right. It's a local circulation in space,
but
but
non-local is a vertical.
exactly. Yep. Yes.
Thank you. I feel sufficiently informed, and before I was not. I'm Wanda Davis. I'm at NASA Ames, and I have a statistical question for you. Mm-hmm. It seems to me that I can see why we would use the mean for this determination on Earth. We have a lot of data. Mm-hmm. However, I think for Mars, the more important statistic is the median. We have very few data points. Mm-hmm. And I'm wondering if you have run all these scenarios, because it seems to be a very excellent and well thought out model, looking at the median and what the outcome might be, if you would care to suggest, or if you've already done it, I'd like to hear.
No, we have not done it yet. It's something that we're actually looking at some of the higher order statistics, including skewness and things like that, because that will help us get to the idea of where is the air really rising? Is it and is the distribution skewed? Are there a few places where the air is really going up quickly, or is it sort of everything is scattered around zero? Or so we are looking at that, but we haven't looked at it in detail yet.
Just another question, and I don't know the answer to this. Is there a way you can take the results from the spacecrafts that we have on the planet and determine the median as opposed to the mean?
Certainly not with respect to the circulation, because we don't have it. So I mean, the data we have are, dust and water and ice clouds and temperatures. So I mean, yeah, you could run all sorts of statistics on it, I suppose, but I haven't thought much about how one would do that or how to apply that. If you have an idea on how I'd be really interested in talking some more with you about that. Yeah.
Hello. That's a very impressive model of local things doing non-local things, and I'm wondering, during the course of the talk, I started thinking about a global phenomena and how your models might interact with, and specifically the height difference in the north and southern hemispheres, and also the periodic global dust storms and how those might interact with your model.
Okay, so the point for those not familiar is that the overall topography of Mars is very different between the northern and southern hemisphere. The northern hemisphere is relatively low, lowlands, and the southern hemisphere is much, much higher and heavily cratered. It's an older surface. And so it's kind of like a step function, right? The south is really high and old and craggly, and the bottom is lower and filled with dust. And in fact, it's been known that difference in height actually produces an asymmetry in the whole overall global Hadley cell. Right? It matters that the south is high. So that effect is certainly there. But this effect also occurs somewhat on the local scale, which is if you take the same mountain or hill or volcano and you put it up here versus down here, you actually get a difference in the circulation. So that does matter. I'm not sure if that's getting to your question, but at any local spot, though, the circulation is dependent on what the whole overall global circulation is doing, plus whatever's happening locally. You can almost sort of add them together, although it's not strictly an addition problem. But so there's definitely a feedback both ways. That is, the small scales I'm proposing contribute to the large scale, but at the same time, there's a very strong control of the large scale on the smaller scales. The small scales do not operate in a vacuum, right? They care what's happening at the bigger scales.
I have the microphone here.
Okay, yeah.
Could you explain how the Martian atmosphere, which is less than 1% as dense as Earth's, do they have much higher winds there? What is it that enables the Martian atmosphere to lift so much dust?
Yeah, that was a perplexing question for a long time, which is, the winds, we think, are in fact generally stronger on Mars than Earth. But if you go through the theory, and more importantly, if you go, let's say, to the NASA Ames Mars wind tunnel, and you crank down the pressure and you fill it with CO2 just like Mars, and then you put down stuff that looks like Mars dust, and then you blow wind over it at about the Mars speed, lo and behold, stuff moves. So, in fact, even though the atmosphere is not very dense at all, the conditions are sufficient to move things around, and we've seen that with dust devils. So, even though it's less dense, the physics do allow stuff to get picked up and moved. Now, we don't understand exactly how that happens fully yet. So there's still a lot of work going on as to exactly how that happens. But the dust is much finer there than here? Is the dust much finer? It can be. We do have some information about size distribution in the atmosphere anyways. We know what the sort of the mean size distribution is based on radiative properties. It's the order of micron size in the atmosphere. In general, though, to move dust, whether it's on Mars or Earth, you actually can't move the dust directly. You have to undergo what's called a saltation process, which means you need bigger grains of stuff like sand-sized particles that start moving. They bounce around, and then they kick up the dust. The dust itself is so small and sits so near the surface that it's almost impossible to pick it up by itself. And this gets back to the original question of, how do we lift dust? It's not just knowing where the dust is. You also have to have a sufficient number of other particles that are big enough to start moving to kick the dust up.
Okay. You talked about the lack of data on Mars. Are future orbiters of Mars going to give us more data, or could they give us more data if they have the right instrumentation?
Yeah. 2 points. The Mars Science Laboratory, which, if you're not familiar, is the next rover that NASA's, as I said, going to launch. I think it's the day after Thanksgiving, day before Thanksgiving, right around Thanksgiving. Will have on it a highly capable meteorology package that is similar but better in ways that we haven't seen since Viking. So it's been about 40 years or so since we've actually measured, really measured stuff on the surface. So we'll have that. It's a long-lived mission. We're going to get long statistics from that, but it's still at 1 point, which is, of course, not sufficient to really give you global information. There are no other missions really planned to be able to bring back the data that we would need to look particularly at the circulation. But there certainly are instruments or missions that could fly, if NASA was so inclined to do so, that could provide really helpful, needed information. And those would be either a network of landers, like we have weather stations on Earth at different places so that you can look at the big picture. Or they could be orbiters that have the correct instruments that profile and look at dust, and even there are instruments that can look at the winds and can provide some of that information. Right now, there's nothing on the books to plan to do that anytime in the next couple decades at least, unfortunately.
I liked your analogy of the thunderstorms on Earth creating a sort of a bimodal distribution of energy and water vapor. But we got a lot of areas on Earth that have a lot of dust in them too. Do you see that sort of two layers with an empty middle layer of dust in the Earth atmosphere too?
In a lot of places you do. So there's two very well-studied source regions of dust on Earth. One is out in the Sahel region of Africa, and the other is in Asia, in the Gobi Desert area. And in fact, there have been studies of that where they fly aircraft to look at the vertical structure of dust, and they do see the stuff getting entrained, primarily in thunderstorms, but other things, and getting pumped up higher. And in addition, they also see lots of chemicals. For example, if you go to Brazil, where they're burning a lot of trees, of deforestation and clearing the land, you see the smoke, and then lo and behold, all of a sudden it's up in the stratosphere, right? But there's nothing in the middle, and it's all gone up through the tropical thunderstorms in the Amazon. And not only that, but it's also taken the carbon monoxide from the fires and lots of other organics and other stuff and spewed it up there, right? And it turns out this transport is extremely important, not just for aerosols, but for chemistry as well. It's a way to get stuff out of the boundary layer and up there. So we do see these layers on Earth. And we see it locally, even in Los Angeles, which is smoky, smoggy. I spent my years at UCLA there. And in fact, when you look at the photochemical cycle and the smog cycle in Los Angeles, if you don't include the flows coming up the San Gabriel Mountains and the interaction of the sea breeze with that, and they actually pump some of the stuff out above the marine layer, you mess it up. You have to have that stuff in there. So it happens. It happens all the time, all over the place.
Last question.
Sorry. Okay, when you think about thunder cells on Earth, they're very obvious. There's something you can see.
Right.
And if you speak of the fixed locations where you've got the big volcanoes on Mars, they should be the loci for many of these. Have we seen anything like what you're talking about with Mars Observer or any of the other Global Surveyor or some of the orbiters?
Yeah, there has been some work, particularly with water, and we do know that the volcanic regions the volcanoes are preferred regions for cloud formation, and so there is some supporting data that suggests that it's not uniform at all. I wouldn't say there's been an extensive amount of studies on that, and less so perhaps even for where the dust is. And part of that is when you're trying to map the overall dust, the biggest source that the spacecraft is seeing is the surface, and there's dust on the surface. And if you're trying to look at dust in the atmosphere that's also near the surface, they kind of look the same. And this is why that Omega study that I showed was really important, because they were able to look at the same region within a day or two, and they could subtract out the surface. But it's a difficult problem to do, to get the small details of where the dust is. But it's probably a study worth doing and looking at, try and pull some of that out. And the idea is, how do you test this with the data that we have? And then maybe that's one way to do it.
Okay, I'm sorry to cut off the questions, but if you have any other questions, please come up and ask them of Scott now.
Yes.
Scott, we have a special memorial antique SETI mug for you in commemoration of your talk. And please join me in
thank you very
thanking
much.
Scott.
Thank you.
Matter.